Welcome to the world of routing algorithms. These algorithms are fundamental to how data finds its way across networks. This presentation will cover the basic approaches to network path selection. Let's start by looking at the main types of routing algorithms. We'll discuss distance vector routing, link state routing, and path vector routing. Let's begin with an overview of routing algorithms. They are crucial for determining the best paths for data to travel through networks. These algorithms strive to balance efficiency, making sure data gets where it needs to go quickly, reliability, ensuring data arrives safely, and scalability, working well even as the network grows. Routing algorithms must adapt to changing network conditions, such as links failing or traffic increasing. They operate at different layers of the network model and support various routing protocols that keep our networks running smoothly. Let's delve into distance vector routing. It is based on the Bellman-Ford algorithm. Routers using this approach share distance vectors with their neighbors. Each router maintains a routing table that tells it the best known distance to each destination. Updates are periodically sent between neighbors to keep the tables current. One of the challenges with distance vector routing is the count-to-infinity problem, which can lead to routing loops. Routing Information Protocol, or RIP, and Enhanced Interior Gateway Routing Protocol, or EIGRP, are examples of protocols that use distance vector routing. Here is the Bellman-Ford equation. The distance from a node X to node Y is the minimum of the cost from X to a neighbor V, plus the distance from V to Y. Now let's explore link state routing. This approach uses Dijkstra's algorithm. Each router builds a complete map of the network, understanding every connection and router. Routers flood link state information to all other routers in the network. This method is more computationally intensive than distance vector routing. However, it offers faster convergence, meaning it adapts more quickly to changes. Open Shortest Path First, or OSPF, and Intermediate System to Intermediate System, or ISIS, are examples of link state routing protocols. The algorithm operates through a series of steps. First, discover neighbors and learn their network addresses. Second, measure the delay or cost to each neighbor. Third, build link state packets with the gathered information. Fourth, flood these packets to all other routers. Fifth, compute the shortest path to all nodes using Dijkstra's algorithm. Let's focus on OSPF, which stands for Open Shortest Path First. OSPF is an Interior Gateway Protocol, or IGP. It's designed for hierarchical network design, allowing for fast convergence. One of its key features is the use of areas. These areas limit link state advertisement, or LSA, flooding, which helps maintain network stability. OSPF also supports variable length subnet masking, or VLSM, and classless inter-domain routing, or CIDR. Plus, it offers authentication support, enhancing network security. OSPF divides a network into areas, including a backbone area known as Area 0. Area border routers, or ABRs, connect these areas to the backbone. Internal routers, or IRs, operate within the areas, helping to manage traffic flow. Now let's discuss path vector routing. This is an extension of distance vector routing. It stores complete path information, which helps prevent routing loops. Path vector routing is commonly used for inter-domain routing, making it essential for the Internet. It supports policy-based routing, allowing for flexible network management. However, it typically has a slower convergence compared to link state routing. The primary example of path vector routing is the Border Gateway Protocol, or BGP. Autonomous systems, or ASAs, are connected. Border routers, or BRs, facilitate communication between ASAs, while internal routers, or RS, manage traffic within each AS. These paths include a list of autonomous systems, or ASAs, that a route passes through to reach a destination. Now let's take a closer look at BGP, which stands for Border Gateway Protocol. BGP is an Exterior Gateway Protocol, or EGP, making it the standard for Internet routing. It operates using Transmission Control Protocol, or TCP, port 179. BGP makes routing decisions based on policies, offering flexibility in network management. While it converges slowly, it provides stable routing across the Internet. BGP supports classless interdomain routing, or CIDR, and route aggregation, helping to efficiently manage IP addresses. It prevents routing loops by using the autonomous system, or AS path attribute. Here's an example of a BGP route entry including attributes like network, next hop, AS path, local preference, multi-exit discriminator, or MED, and origin. Here are some key BGP path attributes including AS path, local preference, multi-exit discriminator, or MED, and origin. Now let's compare the routing algorithms we have discussed. Distance vector uses the Bellman-Ford algorithm. Link state employs Dijkstra's algorithm, and path vector uses an enhanced distance vector approach. Distance vector shares distance vectors with neighbors, link state shares link states with all routers, and path vector shares path vectors with the AS path. Distance vector has a partial view, link state has a complete topology view, and path vector focuses on AS level path information. Distance vector has a moderate to slow convergence speed, link state has a fast convergence speed, and path vector has a slow convergence speed. Distance vector has moderate scalability, link state has limited scalability, and path vector has excellent scalability. Distance vector has low resource usage, link state has high resource usage, and path vector has moderate resource usage. Distance vector is prone to loops, while link state and path vector are loop-free. Distance vector has limited policy support, link state has moderate policy support, and path vector has extensive policy support. Examples of distance vector protocols are RIP and EIGRP, examples of link state protocols are OSPF and ISIS, and the primary example of a path vector protocol is BGP. The choice of routing algorithm depends on the network size, topology, and administrative requirements. Let's summarize the key takeaways from our discussion. Distance vector algorithms are simple but prone to loops. Link state algorithms provide fast convergence but require more resources. Path vector algorithms excel at policy-based interdomain routing. The selection of an algorithm depends on the specific network requirements. Hybrid approaches can combine the benefits of multiple algorithms. Here are some future trends. AI-driven routing uses machine learning to optimize path selection. Secure routing enhances protocols to prevent route hijacking. Intent-based networking translates business requirements into network configurations. 5G and IoT routing creates specialized algorithms for next-generation networks. Thank you. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.